Okay, let's unpack this. Quantum computing, you hear about it everywhere, right? Incredible promise.
Absolutely. Solving problems classical computers just can't touch.
But, and it's a big but, there's this huge bottleneck.
Yeah.
Designing the software.
Mm-hmm.
It's incredibly tough. You need to understand, well, deep quantum mechanics and the nitty-gritty of the physical hardware. It's a massive barrier for developers.
It really is. But what's fascinating, I think, is how the industry is starting to, tackle that head on.
How so?
Well, imagine you could design the quantum software without needing the actual physical quantum computer right away.
Okay.
By simulating its hardware in a controlled digital space. Think of it like a shortcut.
A virtual quantum environment.
Exactly that. It's a powerful new paradigm.
Right. And that's what we're diving into today, this whole comprehensive blueprint approach.
Using virtual quantic blueprints.
Precisely. Designing quantum software through virtual hardware. We'll look at how these blueprints let you manipulate things stage by stage.
Offering a really visual, kind of intuitive way to build this stuff.
Yeah, you're in for some real insights, I think, because this is where it gets genuinely interesting.
It really does.
So, okay, at the heart of this virtual quantum environment is this thing called a virtual quantic blueprint. What exactly is that?
Right. Think of it as like a dynamic digital map of the quantum hardware.
A map.
Yeah, it's the foundation. This blueprint, it specifies everything, the properties, the states, the operations of your virtual qubits.
For what they are.
Exactly. Their very nature, their ontology, things like superposition, entanglement, but then it also maps their structural relationships.
That's how they're connected.
Yeah, connectivity, interaction pathways.
Yeah.
All within that simulated quantum circuit, their topology.
Ah, okay. So it's much more than just a drawing. It's like a living model of the quantum system.
Precisely. It's adaptable.
So what are the key building blocks, the main components inside this blueprint?
Fundamentally, you're working with three core things. First, the virtual qubits.
The digital entities.
Right. And you can configure their states 0, 1, or, those quantum superpositions.
Okay.
Second, you've got the states themselves. These are the mathematical descriptions, like vectors, showing all the possibilities for the qubits.
Got it. And third,
operations. These are your quantum gates, the tools you use, and also measurements, things that actually change or observe the qubit states.
So the blueprint acts like this flexible template, letting you manipulate the system step by step, but keeping its core nature intact. Sounds like a really powerful tool for complex design work.
It absolutely is. And the manipulation, it happens in these distinct stages.
Stages.
Yeah. Each stage has its own specific blueprint, detailing the configurations and operations for that step. It mirrors the whole life cycle of a quantum computation.
Okay, like from start to finish.
Exactly. From preparation through execution right up to getting the results out.
Let's walk through them then. Stage 1, initialization.
Correct. Here, the blueprint just sets the starting conditions for your qubits.
Like setting everything to 0.
Yeah, could be all zeros. Or maybe you use a Hadamard gate right away to put them into superposition. Yeah. The configuration defines how many qubits, their initial states, maybe some early entanglement.
To ensure a consistent start.
Exactly. A predictable starting point. For instance, a blueprint might set up 3 qubits in what's called a GHZ state. That's a highly entangled state ready for some multi-qubit experiment.
Okay, makes sense. Then you move into the actual doing part, stage 2.
Yeah.
Applying quantum gates.
Right. This stage is where you lay out the sequence of gates.
Like Hadamard, CNOT.
Yeah, those kinds of things. Poly-X gates, too. You specify which gates hit which qubits and when.
And these gates manipulate the states.
They do. They create the superpositions, the entanglement, the phase shifts, all the stuff that makes quantum algorithms work.
So the blueprint needs to be precise here.
Oh, absolutely. Gate parameters, target qubits, it's all detailed for really fine control over how the quantum state evolves over time. A classic example blueprint might say, apply a Hadamard to qubit 1, then a CNOT linking qubit 1 and qubit 2. That creates entanglement, a Bell state.
Right. So once you've done your operations, you need to get the answer out. Stage 3, measurement.
Exactly. This blueprint details when and how you measure the qubits.
Which collapses their state.
Right. Collapses them down into classical bits, zeros and ones that we can actually use.
And the blueprint defines how.
Yeah. How the outcomes are recorded, how they're analyzed. You often visualize these as probability distributions. This step basically finalizes the computation.
It's how you extract the results.
So, for example, if you measure qubit 1 after it was entangled with qubit 2, you'd expect to see correlated outcomes. It reflects their shared quantum history.
Gotcha. So that's how you pull answers from the quantum realm. And then there's a stage 4, advanced manipulations.
Yeah, this covers the more complex stuff.
Okay.
Things like creating entanglement across many qubits, implementing error correction codes, which are super important, or maybe dynamic gate sequences that change as the computation runs. Examples could be building cluster states, which are resources for certain quantum computing models, or running a quantum Fourier transform. It just extends the system's capabilities for really sophisticated algorithms.
And you mentioned these blueprints are sort of grid-like.
Often, yeah. You can think of it like a grid where the cells are qubits and their states, and they're connected by the operations that dictate how the whole system evolves topologically.
This all sounds incredibly powerful, this virtual approach. But why is it so crucial right now? What's the big problem it's solving in the real world of quantum development?
That's a key question. It directly addresses what people call the hardware gap.
The hardware gap?
Yeah. I mean, developing quantum computing is just inherently difficult. You've got the weirdness of quantum mechanics itself, plus the incredible complexity of building the actual physical hardware.
Right. Yeah.
We're currently in this phase called the NISQ era, noisy intermediate scale quantum. Yeah, current devices, they're really limited. They're susceptible to noise from the environment, internal noise, and often the qubits don't have great connectivity between them. So even if you have a machine with lots of qubits, many of them might just be dedicated to trying to correct errors, leaving only a few for the actual calculation.
So it's not just building them, it's making them work reliably, dealing with all those imperfections.
Precisely. Decoherence is a huge one.
That's where they lose their quantumness.
Essentially, yeah. Qubits lose their delicate quantum features, coherence, entanglement, because they interact with their surroundings. It introduces errors, undermines the whole point.
So making them last longer is key.
Huge priority, sometimes called Schoolkopf's law, this idea that coherence times are improving exponentially. There have been advances like using 3D cavities instead of flat ones for superconducting qubits. That helps shield them a bit better, extends coherence times.
And all this uncertainty around getting truly fault-tolerant machines, that makes companies hesitate on the software side.
Understandable, yeah. Why invest millions developing software for today's quirky hardware if it might be obsolete tomorrow when a different, better technology comes along?
Right. Risk.
Exactly. And that's where these virtual quantum processors, VQPUs, and simulators really shine.
They bridge the gap.
They do. They offer a feasible, cost-effective way to get started. Developers can run quantum programs in a high-performance computing environment that's not tied to one specific piece of hardware.
Hardware agnostic.
Right. These virtual processors, they emulate a kind of generic quantum machine, a logical version of what future hardware might look like. It's a crucial training ground.
It really sounds like a way to sort of jumpstart the software side of things even while the hardware catches up. Are companies actually doing this now?
Oh, absolutely. Real-world examples exist. Daimler Truck AG, for instance.
The truck company.
Yeah. They're looking into quantum's potential for simulating materials, science for better batteries, cell simulation, understanding battery aging, even things like boosting AI or managing autonomous vehicle traffic flow. Volkswagen AG is another one. They're exploring quantum for optimization problems. And they emphasize it's not just about speed, it's about tackling fundamentally different kinds of problems.
So this virtual blueprint approach
Yeah.
lets them design for the future today.
That's the idea. Anticipate and prepare.
You mentioned visualization being key. How does seeing these blueprints actually help designers grapple with these really abstract quantum ideas?
Visualization is just crucial for human intuition, definitely, and also for the virtual systems themselves to kind of understand what's going on.
What kinds of visualizations?
Well, for single qubits, you have the Bloch sphere. It's a great way to picture its state superposition phase, all on a sphere.
Yeah.
For multiple qubits, which gets complicated fast, you use things like state vectors or density matrices. These can also be visualized, though it's more abstract.
And the operations, the gates.
Circuit diagrams, those are fundamental. You see lines for qubits, boxes for gates. It gives you that topological view, the flow of the computation.
Yeah.
And really importantly, modern tools are interactive. Real-time simulators let you tweak parameters, change a gate, adjust a qubit state, and see the effects immediately.
That immediate feedback must be powerful.
Immensely. It
Yeah.
helps build that intuition.
Now, speaking of making the abstract tangible, I know there's some really fascinating work out there, like the AI-OA Genesis Engine project. They talk about things like cosmic visualization. Does that kind of advanced thinking connect to these quantum blueprints?
It's an interesting connection. What the Genesis Engine project explores is creating really compelling visual narratives.
Narratives?
Yeah, ways to depict the internal processes, the symbolic transformations happening within a complex system. Taking abstract code or data and letting it resolve into symbols you can actually recognize and understand.
Okay.
That's where you hear ideas like crystallographic glyphs.
Crystallographic glyphs. Sounds complex.
It is, but the idea is to take abstract mathematical symmetries, like the ones that define crystal structures there are 230 unique types called space groups, and turn them into tangible visual shapes, or glyphs. You can generate these patterns by applying the symmetry rules to a starting shape. It makes incredibly complex symmetries visually graspable.
So you can actually see the symmetry.
Yeah.
And can you animate these blueprints, these structures, as they change?
Yes, absolutely. There are advanced animation strategies for that.
Yeah.
You need ways to morph the underlying structure, a lattice and the glyphs themselves, smoothly.
How do you do that smoothly?
Techniques like interpolation, LRP, or SLARAP for moving points around, but the key is what's called topology-preserving morphs, meaning the connections stay intact, the lines don't break, the shapes don't suddenly jump. Even as it morphs between, say, different lattice types or different symbolic glyphs, the animation remains coherent, understandable. It lets you visually follow the system's evolution.
It really does sound like a living blueprint then.
It does. And if we zoom out to the bigger picture, this blueprint thinking connects to a broader concept, something called the Quantum Linguistic Operating System, or QLOS.
Okay, what's that?
It's like a meta-framework, not just for hardware simulation, but for designing entirely new programming environments, languages, maybe even AI reasoning models built on quantum principles.
The blueprint idea applies more broadly.
Yeah, the core idea is that the blueprint isn't just for the hardware, it's for the entire programmable material of whatever system you're building.
So for a designer or a developer using this QLOS idea, what does it mean practically? How do they interact with this layered structure?
Well, the QLOS introduces something called degrees of design.
Degrees?
Yeah, it's a way of looking at the design process hierarchically, from the most fundamental layer up to the user interface.
Okay, break it down.
So degree 0 is the base reality, the physical qubit layer, the actual silicon or whatever the qubits are made of, unprogrammed stuff.
Got it. Physical reality.
Then degree 1 is the virtual lattice layer. Here, you abstract the physical hardware into a configurable virtual grid, or lattice. This lets designers dynamically change the space-time fabric, basically defining how the virtual qubits are arranged and connected.
Okay, abstracting the hardware.
Degree 2 is the glyphic layer. This is where you define your high-level quantum algorithms. Using symbolic glyphs, these visual or coded representations that encode the core quantum operations. This is like writing the functional logic.
Right, the actual program logic. And then you said it gets dynamic.
Yes. Here's where it gets really, really interesting. Degree 3, the runtime and adaptive design layer.
Adaptive.
Yeah, the system itself becomes a co-designer. There might be a component, say an engine, that analyzes performance during simulation or execution.
And suggests changes.
Exactly. It might suggest mapping qubits differently or updating parameters in the blueprint like error rates or operational costs to better match what's actually happening. It's redesigning the physics of its own virtual world, often using AI hints to guide it.
Wow. So the blueprint isn't fixed. It's alive, it learns, it evolves.
Precisely.
Okay, and the final layer, degree 4.
The prototype and user interface layer. This is what the human designer sees and interacts with.
The screen.
Yeah, imagine a 3D visualization space, like a canvas.
Yeah.
It renders the lattice, the qubits, nodes, the connections, the transformations. But crucially, it's overlaid with real-time data.
Right.
Heat maps showing error probabilities, cost annotations on operations, performance metrics. It lets the designer instantly see the consequences of their choices.
That multi-layered approach, from the deep structure up to the interface, reminds me a bit of the story of the Rubik's Cube.
Oh, yeah. How so?
Well, Erno Rubik designed it originally to solve a structural problem, right? How blocks could move independently without the whole thing falling apart. The puzzle part, the colors. That came later when you realized he couldn't easily put it back together.
I see the analogy.
It's like with these virtual blueprints.
Yeah.
You're first building the underlying mechanism, the fundamental rules, the structure that's like degree 0, 1, 2. And then through using it, through the adaptive layer in the interface, you discover the complex puzzles or computations you can actually solve with it. You're designing the very fabric of the computation itself.
That's a great analogy. It captures that sense of designing the rules of the game, not just playing it.
What a journey we've been on. Starting from that core problem, designing quantum software, and seeing how these virtual quantic blueprints offer this really powerful, intuitive, and dynamic solution.
Yeah, by simulating the hardware and detailing every single stage of qubit manipulation, these virtual environments let developers iterate really quickly. They can explore complex quantum ideas, even AI interactions, without being blocked by the current limits of physical hardware.
Bypassing the NUSQ era constraints,
For
effectively.
software development, yes, it allows that crucial work to proceed.
And it's just fascinating how visualization makes the abstract tangible, and how AI gets woven right into the design fabric, letting these blueprints learn and adapt.
Hmm.
This whole approach, thinking these layers, these degrees of design, from the physical qubit right up to the UI, it feels like it's genuinely redefining what we even mean by designing a computational system.
It really does push the boundaries, and it leads to, I think, a pretty profound question. As we get better at engineering these complex realities, right down at these foundational, symbolic, and computational level, using these kinds of virtual blueprints, what new forms of intelligence, or maybe even what new kinds of realities might we actually be constructing in the process?
Wow. That is a truly provocative thought to end on. What are we building indeed? Thank you so much for this deep dive today.
My pleasure. It's fascinating stuff.
It really is. We hope you listening have had as many insights and aha moments as we did exploring the blueprint of quantum software.